All right, in this video, we're going to talk about polarity and molecules. Now, in previous videos, you learned how to determine if bonds were nonpolar versus polar covalent. And you did that by using the change in electronegativities between the two elements. So you're going to need your Pauling scale of electronegativities throughout this video. So if we look at a binary compound, for example, hydrogen chloride, we see that the difference between the two species is a 0.9. And again, recall electronegativity is the ability of an element to attract bonded electrons to its nucleus. Recall that chlorine and fluorine and oxygen have some of the highest electronegativities, whereas your group 1 metals have the lowest electronegativities. So we can indicate this using a lowercase delta, just a reminder here. And this is showing an overall partial charge disparity, saying basically that within this molecule, the chlorine, the more electronegative species, it has more electrons closer to its nucleus. And I use the example in class of Skittles. If we have 10 Skittles, and I'm chlorine, then I get 7 Skittles and you only get 3 Skittles. Okay, so again, there's two ways. You can use the lowercase delta with a positive or a negative sign, and you can also use the arrow indicating and pointing toward the more electronegative area within the molecule. All right, but what we're going to do in this video now is we're going to go beyond binary and get into some discussions of ternary structures and even beyond. So a classic example would be water. Water, as you know, is a polar molecule, and we're going to talk about how bond angles and geometry, the overall shape of a molecule, can be used to determine the polarity of a molecule in this video. So we have several points to make before we get into examples. The valence shell electron pair repulsion theory determines the shape and ideal bond angles. All right, so this is a simple idea that the electron-electron repulsions are going to influence the overall geometry of the molecule. And we've talked about that extensively in our Lewis structures as we've gone through the shape sheet and looked at even 6 clouds, having discussions about how lone pairs would exhibit an overall greater electron-electron repulsion on surrounding species. All right, so it's no surprise that the shape will determine the polarity of a molecule. Now, where we're heading with this is overall the reactivity of these molecules. So the shape and the geometry, the symmetry will determine the polarity of the molecule. And as I just mentioned, it's the polarity that is then going to affect the physical and chemical properties. Okay, so shape and polarity of each bond must be taken into consideration. So when we look at a ternary structure, we need to look at the individual bonds. In the example of water, we need to look at the hydrogen-oxygen bonds, the hydrogen-oxygen bonds. And then we need to look at the overall shape of the molecule. In the example of water, it has 2 lone pairs and it has a tetrahedral bent geometry. All right, so we need to consider those things. And as you've learned throughout this course, there's also exceptions, and we're going to get to some of those when we start looking at even more complex molecules, where there's actually parts that are polar and regions that are nonpolar, okay, which is a reality. So carbon dioxide, okay, structure of carbon dioxide. All right, so when we look at this molecule, we can say, all right, overall, it has a linear triatomic shape, okay? Bond angles of 180 degrees, no lone pairs, so it is symmetrical. Carbon, if you look at your scale, is a 2.5, and each oxygen is a 3.5. So a delta En for each of these bonds is equal to 1, which puts us into the polar range if you're using the scale at the bottom of your electronegativity. But now we need to take into consideration the overall shape and how that would influence it. So I would use the analogy of a tug of war. Carbon's in the middle, and I'm oxygen, and I have a 3.5 on a relative scale, on a qualitative scale, and you're the other oxygen on the other side, 180 degrees between us, so a straight line from me to you, and we're going to have a tug of war. Well, who's going to win? Nobody, because we're both 3.5. So in this case here, the polarities are going to cancel out. It's going to cancel, resulting in no overall dipole forming, and a molecule that is non-polar covalent overall. Even though its individual bonds are polar covalent, the molecule is non-polar covalent. Now let's look at water. Oops, all right. Let's look at water here. All right, so when we look at this structure, which I already said, there's 4 electron groups, 4 clouds, tetrahedral, the geometry, bent, 104.5 degree bond angle, but I want you to understand that it is less than 109.5 and even a little less than 107, 106, so 105-ish, 104.5 is the actual ideal bond angle here. So in this case here, we have our hydrogens coming in at a 2.1, 2.1. We have a 3.5 here, and we have an asymmetrical molecule. What we're going to end up with is a slightly positive region and a slightly negative region here. And we're going to talk about this throughout. This is a polar molecule. This will have a slightly negative and a slightly positive charge across the molecule. Thus, we refer to molecules that exhibit this dipole moment as polar. All right. So here are the steps. I want you to write these down. Step number 1. If the molecule is nonpolar and symmetrical, and all of the outer peripheral atoms are the same, the dipoles cancel out. And we saw that with carbon dioxide. Okay? Think of the tug of war example. Now, here's a trigonal planar. Think of a 3-way tug of war. All right? Remember, this is up on the plane. So 3 now having a tug of war. The yellow atoms could all be hydrogens, all of equal strength, and they're having a tug of war. Who wins? Nobody, because each dipole, essentially the direction, these are vector quantities, we don't need to get into that, but they cancel each other out. So the tug of war analogy works really well. So in this case here, it is symmetrical, and all species are the same. This is non-polar. Okay, step 2, if the shape and the symmetry are not the same, then the changes in electronegativity have to be used, and that has to be done on a case-by-case basis. So you literally need to get out that Pauling scale, and for each individual bond, look at what the change in electronegativity is. Use that scale from 0.5 to 2. Recall that from 1.7 to 2, it could either be a polar covalent or ionic, depending on whether or not it's bonded to an atom or excuse me, a metal or a non-metal. All right. Step number 3, if the shape is asymmetrical, if it is not symmetrical, then all peripheral and all peripheral atoms are not the same. It's polar. All right. So we saw that one with water. It had that bent asymmetrical shape. So those lone electron pairs on the central species are often going to result in an asymmetrical shape and therefore a polar molecule. All right. So here's an example of an asymmetrical shape. Even though this has a total of 3 electron clouds, but it has this structure where it is now bent because of those lone pairs on the central species and that decrease in the ideal bond angle from, say, 120 to, in this case, 119. All right. Step number 4. If the shape is asymmetrical and all of the outer atoms are identical, then the molecule is still probably going to be polar. But there are exceptions that you know I will get to. Okay, so let's do several examples. Is the molecule polar or non-polar? Let's look at this. Start with ammonia. Pause the video, do the whole Lewis structure, go through, even if we've done this in class, go through and do it again, calculate formal charges, all of that fun stuff. Okay, all right, so... All right, here's the overall structure. Then say, how many clouds does it have? Okay, it has 4. Well, does it have any lone pairs? Sure it does. All right, so now let's look at the 3-dimensional form of this, okay? So would you say it's asymmetrical? Sure, absolutely. Absolutely it's asymmetrical, okay? If you look at the differences in charges here, so our hydrogens are all 2.1, but this guy in the middle here is a 3.0, and it's asymmetrical. So 2.1 and back here 2.1. So what's that going to do? It's going to leave down here, it's going to leave or result in a partial positive charge, whereas this direction we're going to have a partial negative charge. And again, you can use the lowercase delta to indicate that. So the answer is yes, ammonia is polar. Why is it polar? Foremost, it's asymmetrical. All right, as a result of that lone pair. In addition to that, there's an overall net dipole that's occurring here. You can also indicate this as such, each individual one. But overall, the direction is pointing toward the more electron-dense region of the molecule, which is as indicated right here. Okay? All right. Is the molecule polar or non-polar? Let's do boron trichloride. I'm going to redraw that so it looks a little more symmetrical on my end here. All right, so we have all of our octet rule fulfilled. We have boron. Boron is good to go with 6, so it can have an incomplete octet. There are 3 electron clouds. There are no lone pairs, so we have a trigonal planar molecular shape here. If we look at our electronegativities, we have 3.0 on these outer peripheral species here. And you might be saying, hey, wait a minute. That's polar. That's polar. Yes, the bonds are polar, but the molecule is nonpolar, because if you think of our tug-of-war analogy of all of the outer species having the same relative strength or ability to attract bonded electrons to their nuclei, they cancel out. So this molecule is nonpolar foremost because of its symmetry, but also because all dipoles will cancel out. And again, due to its symmetrical shape. So chloromethane, is it polar or non-polar? So I've given you the formula for this one. All right. Go ahead, pause, give it a shot. And that's an H there. Chlorine right here. And our chlorine, let's see, 1, 2, 3, 4, 6. Okay, so there's the structure. Count the clouds. There are 4 clouds. This is a tetrahedral. Are there any lone pairs? No, there aren't. Okay, so it's a tetrahedral shape. This electron group shape is symmetrical. Okay, however, all peripheral species are not the same, so we need to look at the individual dipoles that are being set up here. Okay, and you can see the electronegativity values that I have here with 2.1, 2.5, and 3. So overall, there is a net dipole. Another way you can think of it again is as if, you know, we have a partial positive charge in this region here, and then up in this region here we have a partial negative charge. Okay, so chloromethane is polar. Even though it is symmetrical, the dipoles are all pointing toward the region of the chlorine, therefore resulting in an overall net dipole for this molecule. All right, formaldehyde. Formaldehyde. I've given you the formula here. Pause the video, give it a shot. Okay, structure for formaldehyde. All right, so if we look at its shape, its molecular shape is trigonal planar. There are no lone pairs on the central atom. Remember, multiple bonds still just count as one cloud. Okay, so we can now look at our individual electronegativities. All right, so our hydrogens are 2.1. Carbon 2.5, and we have a 3.5 here. So if you look, would you predict, despite its symmetry, that this is polar or non-polar? All right, so again, you want to look at, there's very minor, 0.4, 0.4, and if we were only looking at the bonds, we would say non-polar. But we're looking at the overall dipole that's being created here, and we have a beast here. We have a delta En of 1.0, which is going to result in a dipole moment, which means that this molecule is polar. Again, it is symmetrical in its shape. However, when we look at the individual case by case, the different bonds going on here, the carbon-hydrogen bonds and the carbon-oxygen bond, overall our dipoles are pointing in the direction of the oxygen, resulting in an overall net dipole. So formaldehyde is a polar molecule. All right, so now I want you to go through your problem set and use the shape and geometry of the molecules that you've already worked through. And I want you to determine, is the molecule polar or non-polar? And I'll see you guys in class.